Hi everyone! In this video, we're going to start learning about polynomial functions. As an introduction to this topic, we're going to start by analyzing these four basic functions and their graphs. What is the graph of the basic square function? Well, it's the parabola that opens up and has its vertex at the origin. Now, what happens if we put the negative sign in the front of the basic square function? Well, the graph will be reflected and the parabola will open down. Here's the graph of the basic cube function, and if we place the negative sign in the front, the graph will be reflected over the x-axis. Let's spend a little bit more time on describing the end behavior of those graphs. First, let's note what we have already observed. In the graph of the basic square function, both ends go up. For the graph of the square function with the negative sign in the front, both ends go down. What can we say about the graph of the cubic function? In this case, the right end goes up and the left end goes down. For the cubic function with the negative sign in the front, the left end goes up and the right end goes down. How can we say all that mathematically? There are at least two ways to do that. For example, to show that for the graph of the basic cube function, the right end goes up and the left end goes down, I can say the following. As x approaches positive infinity, this arrow we read as approaches. What it means is that as x values are increasing towards the positive infinity, function values or y values also approach positive infinity. So as x values increase, the y values also increase. How about the left end? Well, we'll say the following. As x approaches negative infinity, it means that as x values get smaller and smaller and smaller, so we're moving to the left. F of x, or function values, or in other words, y values, also approach negative infinity. In other words, this left end goes down. Let's try this for the rest of the functions and their graphs. This is how we're going to describe the end behavior for the basic square function, where both ends go up. As x approaches positive infinity, function values or y values also approach positive infinity. That's this right end. And as x values approach negative infinity, so they get smaller and smaller, function values approach positive infinity. That's going to be the left end. As x values get smaller, y values get bigger. Here's a description of the end behavior of the graph for the function negative x squared, where both ends go down. When x approaches positive infinity or negative infinity, function values approach negative infinity. That's why we have this downwards direction. And finally, the description of the last graph, f of x equals negative x cubed. And I'm going to show you one more way to describe the end behavior of those graphs. That method involves using the limit. Look at this first expression, and this is how we read it. Limit of f of x as x approaches positive infinity equals to positive infinity. And that's this first description. Here's the second one, limit of f of x as x approaches negative infinity equals positive infinity, because remember how I said as x approaches negative infinity, function value approaches positive infinity, right? So hopefully you see the connection between those two. It's just instead of writing this part with the arrow representing the word approaches, we use the limit notation. At this point, you might want to pause the video and try to figure out if you can create the rest of the descriptions using the limit notation. And here are the answers. So besides observing the end behavior for the four given functions, let's also talk about the characteristics of the graphs. Let's note that all four graphs are smooth and continuous. Let me give you counterexamples. For example, graph of the function y equals absolute value of x is not smooth. See how it has a sharp corner over here? And the graph of this piecewise defined function is not continuous. Notice that there is a gap here. In other words, I won't be able to trace this graph without lifting my hand. Okay, so we analyzed the end behavior of the graphs of these four functions, and we also observed that they're smooth and continuous. And here's the question. What if we increase the powers in these functions and add more terms with various coefficients? What kind of function and the corresponding graph will that be? And here's what I mean. What if we consider a function that has the highest power 7, it has more terms involving x raised to different powers and different coefficients? Well, that's going to be an example of a polynomial function. In fact, all those four functions that we looked at, they're also special cases of polynomial function. And it means that everything that we observed about their graphs will stay true for any other polynomial function that we work with. I'll show you the examples. But first, let's look at the formal definition of a polynomial function. So a polynomial function in one variable is a function of the following form. Let's try to understand what we see here. First of all, we can see that this function involves different terms. And most of those terms have variable x, well, except this last one. Right in front of each variable x, we have a coefficient. They are denoted by a sub n minus 1, and so on. These are the real number coefficients. The very first term contains x with the highest power, and the highest power determines the degree of a polynomial. Please note that all powers must be whole positive numbers in order for this kind of function to be a polynomial function. The term containing the highest power of x is called the leading term, and as a result, the coefficient in that term is called the leading coefficient. Here it's a sub n. And the term that does not contain x is called a constant term, because it's just going to be a number here. Let's do the following example and practice recognizing a polynomial function. So we determine which of the following are polynomial functions, and for those that are, we'll need to state the degree of a polynomial. So what can we say about this first function h of x? The first thing to check is whether the powers are the whole positive numbers, and they are. So here we have power 4 and then power 2. And whether the coefficients are real numbers. Well, they're all real numbers. There are no imaginary numbers here. So yes, this is a polynomial function. Now, what's going to be the degree? Remember that the degree of a polynomial is the highest power of x. In this case, it's 4. And that means that 4 will represent the degree. How about the next function, g of x? Let's check if all powers are the whole positive numbers. Well, in this case, they're not. There is a term with square root of x, which is the same as the x to the power 1/2. This means that the power of x is a fraction. It's not a whole number. So g of x is not a polynomial function. And finally, function p of x. Is this a polynomial function? As far as the powers, we can see that they're all whole positive powers. However, it's not written in the standard form where we can see the collection of terms. That's true. However, we could rewrite it in this form, right? If I square expression x plus 4, and then if I multiply each term by 1/2 x to the power 5, then this function will be in the standard form where all powers are the whole numbers and with real coefficients. Now, how do we determine the degree of this polynomial? Well, that has to be the highest power of x. Again, imagine simplifying this expression. Once you square x plus 4, what's going to be the highest power in that expression? Well, it's going to be x squared. And then x squared will be multiplied by x to the 5th power. So what will be the resulting power? It's going to be 5 plus 2, which is 7. So yes, that's a polynomial function of degree 7. And to see the highest power, you would want to simplify this expression. Okay, so once we look at different examples of polynomial functions, let's talk about their graphs. We can learn how to graph a polynomial function in the next video, but for now, let's connect what we talked about at the beginning of this video, and let's discuss the end behavior of a graph of a polynomial function. Remember how we talked about the graphs of these basic square and cube functions, and we observed their end behavior. We also talked about how these graphs are smooth and continuous. Well, since these functions are just the special cases of a polynomial function, it means that in general, the graphs of all polynomial functions will behave same way. So they will be smooth and continuous, and while they can take very interesting curves, the end behavior can still be put in 4 different groups. Here they are. Graphs where both ends go up, graphs where both ends go down, graphs where the left end goes down and the right end goes up, and the other way around, graphs where the left end goes up and the right end goes down. So I'm going to show you how to determine the end behavior of a graph of a polynomial function by just looking at that function. And when we're going to learn graphing, knowing the end behavior will be the very important piece of information. And this is how you will know the end behavior. Let's look at this first sketch where both ends go up. Let's think what basic function that we looked at the beginning of the video had a similar end behavior. Well, it was the basic square function, right? Now remember that polynomial functions can have higher powers and they can have coefficients, but let's use this basic square function to generalize this case. So basically any polynomial function with even highest power and positive leading coefficient will have that same end behavior. Let's try it for the next one. What is the basic function that we looked at has the same end behavior? It's the function y equals negative x squared, right? What can we say about the power and the coefficient? Power is even and coefficient is negative. So it means that graphs of all polynomial functions with even highest power or even degree and negative leading coefficient will have the same end behavior. In other words, both ends will go down. Let's go to this case. Such end behavior, left end goes down, right end goes up, is the same as we observed for the graph of the function y equals x cubed, which has odd power and positive coefficient, positive 1. So that means that graphs of all polynomial functions with an odd highest power and positive leading coefficient will have this end behavior. We will learn how to figure out what happens here, how many turning points the graph will take and all that, but at least for now we already know what the end behavior is going to be. And here's our last case. So this kind of end behavior, left end goes up, right end goes down, is the same as for the function y equals negative x cubed. It has an odd power and negative coefficient. So graphs of all polynomial functions with odd highest power and negative leading term will have that same end behavior. Let's practice this. In the following example, we're given two polynomial functions and we need to determine their end behavior. By now, we already know that to determine the end behavior, we just have to look at the highest power or the degree of a polynomial and the leading term. In our first example, the highest power is 4 and it's even. Now the leading coefficient is negative 0.3 and it's negative. At this point, I want you to think about one of those basic functions from the beginning of this video and think which one had same properties, even index, negative coefficient. Well, that was the function y equals negative x squared, right? Do you remember its graph? It's the parabola that opens down. In other words, both ends go down. Well, that means that the graph of this polynomial function will have same end behavior. Both ends will go down. Let's write this down using the limit notation. So limit of the function f of x as x approaches positive infinity, it means that we're talking about the right end, equals negative infinity, which means that the right end goes down by values approach negative infinity. And limit of that same function f of x as x approaches negative infinity, which means that we're talking about the left end, is also negative infinity. Both ends go down. Okay, let's try function g of x. What can we say about its highest power? Again, this function is not given to us in standard form, so technically in order to find the highest power, we need to multiply everything out. But we can use the shortcut and just think of what would be the highest power if we multiplied everything out. If I raise this first expression to the power of 4, then the highest power there will be 4. Here the highest power of x will be 2, and here the highest power of x is 1. Once I multiply everything out, the highest power of x will be 4 plus 2 plus 1, which is 7. Remember, when we multiply same variables, their powers get added. Okay, so the highest power is 7, which is an odd power. What is the leading coefficient? And we technically only need to know its sign, positive or negative. So once we multiply all the coefficients, actually it's 6 over 7 and then 3 that we'll have to multiply, we see that it's positive coefficient. So now think of a basic function from the beginning of the video that also had an odd power and positive coefficient. Well, it's the function y equals x cubed. What is the graph of the function y equals x cubed? Well, it has this shape, with the right end that goes up and the left end that goes down. Well, the graph of this polynomial function will have exactly the same end behavior. Now let's try to write this answer using the limit notation. This time I have to say that limit of function g of x as x approaches positive infinity. Basically, when we describe the end behavior using limits, we always have two limits In one of them, x approaches positive infinity, that's describing the end behavior of the right end, and x that approaches negative infinity, that's describing the left end of the graph. So we said that the right end goes up, so it means that y values or function values approach positive infinity. And for the left end, in other words, when x approaches negative infinity, function values or y values approach negative infinity as well. Okay, so we learned how to recognize a polynomial function, and we already know something about their graphs. First of all, we know that the graphs of polynomial functions are always smooth and continuous, and we also know how to determine the end behavior. In the next video, we're going to start graphing a polynomial function.